let's try this again. So today we're going to be continuing to talk about angle relationships as they apply in circles. So we're going to do several different theorems today. The first one is a lot like an inscribed angle. If you have a tangent and a chord that intersect at the point of tangency, then the angle formed is half the measure of its intercepted arc. These are not inscribed angles because their sides aren't both chords of the circle. Wow, she's really staring. There we go. They're not inscribed angles, but they act like inscribed angles. And the reason is pretty straightforward if you think about it for just a second. If you look at this picture, really. There we go. So if you look at this picture, angle SUN intercepts arc SU. That arc is inside of that angle, right? And angle SUY intercepts this big arc over here, SDU. What do those two arcs add up to? This arc over here, 360, right? And what do these two angles add up to? Does it make sense that each angle should be half of the arc? It does. Okay, and that is what happens here. So let's take a look at this example. We want to first of all find the measure of angle EFH. So line FE is a tangent, FH is a chord drawn to the point of tangency. So notice that arc FH is inside of that angle. So this angle is just going to be 65 degrees. It's just half of the 130. Now, if we're trying to find the measure of arc GF, it'd be nice if we knew the measure of angle FG, whatever point is out here. And we can find that pretty easily just by subtracting 122 from 180. That's 58 degrees. Since the angle is half of the arc measure, then this arc should be how much? 116. Yeah, it should be 116 degrees. We could actually also find the measure of angle GFH. Since we know these two arcs, we know the last remaining arc of the circle, we could find that and then divide by 2 to find the measure of the inscribed angle. Now, here's where the problem comes in before we even move on to the next theorem. Students sometimes will overgeneralize. They'll say if the vertex of the angle is on the circle, then the measure of the angle is half of the arc that it intercepts. And that's true most of the time, but it's not true all of the time. If you will, please turn to that secondary page that I gave to you. So here, if we're looking at angles DBE, so this angle over here, and I'll do it in a different color, angle CBF. Those two angles are clearly vertical angles, right? So we know that they're congruent to one another. Now, if those two are congruent to each other, and now if we look at the arcs, arc DB is in the interior of angle DBE, and arc CB is in the interior of angle CBF. Are those two arcs the same size? No. Not even close. So there's no way that this angle is half the measure of this arc. It will not work. There are actually two different ways that you can find the measure of these angles though. One way, the most straightforward way, if you have enough information, and you usually do, is find this inscribed angle by taking half of the measure from C to D. Then these two are just a linear pair and you're on your way. So let's say that this arc was 110 degrees. Then this would be 55 degrees, and we would subtract that from 180, and this would be 125 degrees. Now, there actually is another way that you could do this. Let me get rid of these. All right, so we need to measure for arc DB. I don't know. That's a little small. Well, let's see. A right angle would be like that. It's a little less than that, so let's say that it's 70.
That was close.
Yeah. And over here, this is less than a semicircle, but it's definitely more than 90, right? So let's say that it's, I don't know, I'm going to say it's 140. And you don't need to write all this down, just let's follow along. So if that's 70 and that's 140, together that makes 210, which leaves how much for this arc over here? 150. If that's true, then this is 75, and this is, subtracting from 180, 105, right? This would also be 105. Here's the interesting thing. If you take 70 and 140 and add them together, what do you get? 210. How is 105 related to that? It's half. This arc is too small, this arc is too big. We average them out and we can get those angles. So if it's an inscribed angle, or the vertex is on the circle and one of the lines is a tangent line, then it's just half the arc that it intercepts. But if it's not, you're going to have to do something else. Okay, let's go back to the notes. So this one says if two chords intersect in the interior of a circle, then the measure of each angle formed is half the sum of the measures of its intercepted arcs. So angle GCL is going to be half the measure of arc GL on the left, plus the measure of arc IT on the right. Now, I want to show you why this works. Unfortunately, the program that I'm going to be using cannot be used on my computer any longer. When Mac updated not too terribly long ago, it stopped working on Macs, but it still works on a PC. So here we have this angle AXB. It's going to stay 40 no matter what I do on this one. I have it set up so that no matter how I pull it, it's going to stay 40. Notice the measure of arc AB is 40, and the measure of its vertical angle is also 40, right? What kind of an angle is AXB right now? Nope. Where's its vertex?
Central angle.
Yeah, it's a central angle. Okay? Now, notice here, and I'm going to drag it. If I start here, what's happening as I move this to the right? What's happening to arc AB?
It's getting bigger.
It's It's getting bigger. What's happening to arc CD? Getting smaller. In fact, that's an interesting development. That's weird. Okay. It turns out, I'm gonna drag it somewhere else. How much smaller is arc CD than it was? Well, it was 40 and now it's 22.6. So that's what, 17.4? How much larger is AB than it was? 17.4. Oh, hey, one of them got bigger, one of them got smaller. How do we deal with that? We average them. So that's what we're going to do when the vertex is in the interior of the circle. You're going to have one arc on one side that's too big, one arc that's too small. So you average them out so you can be like Goldilocks and say, oh, that's just right. So back to what we were looking at. Okay, I was afraid it wasn't going to work. So we can also do that with angle GCI. This angle intercepts this arc, which is too small. But its vertical angle intercepts this big arc over here, which is too large. We just average those two and we get the measure of the angle. So for example here, we're trying to find the measure of angle AED. Well, AED, we don't know anything about its arc or its vertical angles arc. So instead, what we're going to do is find the measure of angle AEB. The measure of angle AEB is going to be half of the arc that it intercepts, which is 139, plus the arc that its vertical angle intercepts. Remember, one of them got bigger, one of them got smaller. So it's going to be half of 252. So dividing by 2, that's 126 degrees. And then subtracting the 180 minus 126 leaves us with what, 54 degrees for the measure of angle AED. Occasionally a student will ask me, do I have to find this other angle first? The answer is actually no. I think it's a little more cumbersome to do it the other way, but what do we know about these four arcs in this circle? They add up to 360. So 139 plus 113 plus the measure of arc AB plus the measure of arc CD is 360. DC, sorry. No. Oh, my fault. AD and BC. So those four arcs are going to add up to 360. These two add up to 252. So if we subtract, that's 108. And then this angle, AED, is half the sum of those two. So it's half of the 108, so it's 54. You can do it either way. Okay, whatever appeals to your brain first. Neither of them take terribly, terribly long, especially if you're using a calculator to help you with, adding and dividing and all that kind of good stuff. All right, we're going to go back to my sketch over here. So as I continue, let's see if this is working, to drag point X further and further to the right, what's going to happen to CD? It gets smaller and smaller. If I got all the way out, and I'm not going to be able to do it perfectly, but if I hit the circle, what would happen to CD? It'd be 0. All right, now what if I keep pulling? Now what's happening to CD? It's getting bigger. What about AB? It's also getting bigger. Wait a minute, now they're both getting bigger. Okay, let's go back for just a second. If CD is positive here, and it's 0 right there, if something is positive, then 0, and you kept going in the same direction, what should it be next? Negative. Should be negative. What's 131.2 minus 51.2? 80. Oh, so now if we consider CD to be negative, it's the same idea. So we're just doing the big arc minus the little arc instead of plus now, because they're both getting bigger, so we want to subtract. So that works anytime the vertex is outside of the circle. We can take the big arc minus the little arc and divide by 2. Now the question becomes, how do you know which one is the big arc? The big arc will always be the one that's further away from the vertex, because as the angle moves away from the vertex, the sides of the vertex get further and further apart. The sides of the angle get further and further apart. And the smaller one will always be the one closer to the vertex. So, this is really cumbersome. Get this next theorem. If any combination of secants and tangents intersect in the exterior of a circle, then the measure of the angle formed is half the difference of the measures of the intercepted arcs. And the bigger arc is always the one further away from the vertex. The smaller one is always the one closer to the vertex. This looks a lot like the one we just looked at. The measure of angle C would be half arc AE minus arc BD. Here, now this has gotten to the place where this is a tangent. It's still half of the big arc HI minus the smaller arc GI gives you the measure of angle F. And then if you continued to work with it, you could get it to where they're both tangent lines. Now this one gets to be interesting because these two arcs, arc MK and arc KLM, add up to how much? 360. It's the whole circle. So if we know that, we only need to know one of these two arcs to find the measure of this angle. All right, let's try a couple of problems here. Here we're looking for the measure of angle C. To find the measure of angle C, its vertex is in the exterior of the circle, so it should be half the difference of the two arcs that it intercepts. We've got the smaller angle, but we don't have the larger angle yet. Or we can find it, because what do we know about the arcs in a circle? They add up to 360 all the time. So 85 plus 74 is 159 from 360 is 201 for this arc over here. So the measure of angle C will be half of 201 minus 74. So that's half of 127. So that'll be 63.5 degrees. This next one is pretty involved. You actually have to do two different things in order to get to arc YZ. Let's see what we can do with it to start. If we're looking for the measure of arc YZ, well, its measure would be involved with this 113, right? And we know that this arc over here is also 113, or this angle over here is also 113. And using linear pairs, each of these would be 67. Unfortunately, we don't know what the measure of this arc from W around to this point is. If we did, we would be in business, but not so much. However, and I'm going to name this point because it's going to be helpful to us. Let's call it R. I can find right now the measure of arc RY. Because see how these two 67s intercept RY on one side and WZ on the other side? So that means that 67 is equal to half of the two arcs added together, 68 plus the measure of arc RY. So multiplying by 2, that's 134 is equal to 68 plus the measure of arc RY. Subtracting and we get 66 is the measure of arc RY. Well, now that we have that, if we switch over and use the 49, which is vertex is in the exterior, it intercepts this 66 degree arc that we just found, and it intercepts YZ, the one that we desperately are looking for. So here, when the vertex is in the exterior, the measure of the angle is equal to half of the difference between the two arcs. So the measure of arc YZ minus 66 degrees. Let's see, we'll double that and that'll be 98. And then we'll add 66 to both sides. So 164 degrees is the measure of arc YZ. If you wanted to, you could check yourself on this to see if that makes sense. We know all the arcs in the circle except for arc. If we just look at this, let's see if that fits the measure of arc RW. So let's see, 66 and 68 is 134 plus 164 would be 298. Which would then mean that this arc, subtracting that from 360, would be 62. Let's see, 62 and 164 is 226, cut in half is 113. Okay, any questions about that? All right, your assignment is in the book.